Hello mathematicians, thanks for joining me again today. We saw last time that when we were looking at the function f of x equals x times x minus 2 cubed, we were able to find the intervals of increasing and decreasing, the critical points, and the local extrema. Today what we're going to do is we're going to continue with that, and we're going to instead find the intervals of concavity. That is, where is this concave up and concave down, and if there are any inflection points. Now, the process will be similar in that we will find points where something is 0 or undefined, somewhere where it's positive or negative, we'll make a number line, except this time instead of looking at the first derivative, we're going to be looking at the second derivative. Since we're going to need to look at the second derivative, what I've done is I've found it. In order to find this, remember that we'll have to take the derivative, and then we'll have to take the derivative again. If you'd like to go through that process, I'd refer you back to our previous videos where we went through examples of derivatives, or look at the written version. I do walk through this. But eventually, if we take a derivative, we simplify, we get the second derivative is 12x minus 12 times x minus 2. Therefore, if we want to find where this is positive or negative, what we have to find is where it's 0 or undefined. So I'm going to start off with where is my second derivative undefined. Now, if I look at this, what I have is that this is a polynomial times a polynomial, so it's a polynomial. The domain of polynomials is all real numbers, therefore this is always defined, so this never happens. That is, my second derivative is always defined, so we don't need to worry about this case. On the other hand, we do have to worry about when is the second derivative equal to 0, and that happens if 12x minus 12 times x minus 2 is 0. And so a product is 0 if one of the terms is 0. So that is 12x minus 12 is 0, or x minus 2 is 0. So that gives us that 12x is 12, or x is 2. And so what I get is that I have that my derivative is 0 at x equals 2, or if I divide by 12, I get x equals 1. So my second derivative is 0 at the points x equals 2 and 1. Now I should check to make sure these are in the domain, but my original function is a polynomial. The domain is all real numbers. Therefore, these are both in the domain. Now, we don't necessarily know if they're inflection points yet or not because we have to determine if the concavity actually changes, but they are potential inflection points. And so they're going to end up on a number line that we partition the real numbers into when we're talking about whether the second derivative is positive or negative or 0. So now if we want to find out where is the second derivative positive or negative or 0, we know it's 0 at 1 and 2. So these are the only places that we can change from positive to negative. So it's either always positive here or always negative here, and that's true for each of these subintervals that I partition my real number line into. So what I want to do is just figure out what it is at any one of the points in this subinterval, and then it has to be the same for all the points. So that is, I'm going to find the second derivative at some point that's less than 1, let's say 0. So that sounds like an easy one to calculate. If I do that, I get negative 12 times negative 2 is positive 24. I'm not really worried about the answer itself, I just want to know that it's positive. So what that tells me is that my second derivative is positive on the interval negative infinity to 1. If I pick something between 1 and 2, say 1.5, what we end up getting is, well, if I put 3 halves into the second derivative, I get 12 times 3 is 36 divided by 2 is 18, minus 12 is 6, times 3 halves minus 2 is negative 1/2. So 6 times negative 1/2 is negative 3. That is, it's going to be a negative number. So my second derivative is going to be negative between 1 and 2. Now lastly, I'm going to pick something above 2. So let's say 3. So f double prime of 3 is 12 times 3 is 36, minus 12 is 24. 3 minus 2 is 1. 24 times 1 is 24, which is positive again. So what I get is my second derivative is now positive on the interval 2 to infinity. So now that we have our number line, we're able to determine where is this function concave up, concave down, and what are the inflection points. And so remember, my function is concave up if my second derivative is positive. So our second derivative is positive on the interval negative infinity to 1, union 2 to infinity. So that would mean that my original function is concave up on that same interval. In the same way, my second derivative is negative on the interval 1 to 2, so I'm going to say that my function is concave down on the interval 1 to 2. Now to find the inflection points, what we need to remember is that the concavity actually has to change at those points. And so if I look at x equals 1, notice that I change from concave up to concave down, so I do have a change of concavity. Again, the second derivative is 0 here, and 1 is in the domain of the original function, so we do have an inflection point at 1. So we have an inflection point of 1 for x, and now because of the point we need a y value, so it's going to be f of 1. So what we're going to get is we're going to have an inflection point at 1, and if I plug 1 in, I get 1 times 1 minus 2 is negative 1 cubed is negative 1. So we have an inflection point at 1 and negative 1. Now we also have the concavity changing at 2 from concave down to concave up. So that's going to give me another inflection point at 2, f of 2. So we're going to get 2. And if I plug 2 into the function, I get 2 times 0 is 0. So we also have an inflection point at 2, 0. So now what we see is that our function is concave up on negative infinity to 1, union 2 to infinity. It's concave down on 1 to 2. And I have inflection points at 1, negative 1, and 2, 0. Thank you for joining me today. I hope you enjoyed it, and I hope you learned something along the way. Make sure to subscribe to the channel and like the video.